Okay, so can I start?
Yes.
Okay. So welcome to the session of quantum security. I am Akinori Hosuyamada and will serve as the session chairs with Andreas Hülsing. This session has 7 talks. Each talk is given 5 minutes, followed by 5 minutes Q&As. If you have any questions on the talks, please write them on the Julep chat or the chat of Zoom. And so the first talk of this session is on the non-tightness of measurement-based reductions for key encapsulation mechanism in the quantum random oracle model by Haodong Jiang, Zhenfeng Jiang, Jiang, and Haodong Jiang will give a talk. Haodong Jiang, are you ready?
Okay, I'm ready. Hi.
Okay, then please give your talk.
Okay.
We saw your slides for a moment there.
Okay, sorry.
If you have any technical difficulties on showing your slide, I would like to move you to the last of this session.
Are you able to share your screen?
Okay, let me try again. I'm sorry. Okay.
That looks good.
You should do it in full screen mode.
Okay.
Yes.
Okay. I'm sorry. I'm talking about the paper on the non-tightness of measurement-based reduction for CAM in the quantum random oracle model. This is a joint work with Zhenfeng, Zhang, and Zhang. So the quantum cryptography is to design classical crypto systems that remain secure for a quantum adversary. Recently, NIST launched a PQC project and published a call for proposal for PKE signature and CAM. In particular, more than half of the submissions are CAMs. In these submissions, they first construct a CP secure PKE and then use a generic transform called a Fujisaka model to build a CC secure CAM. We usually call such a transform by FO in short. FO-like generic constructions are based on an idealized model called the random oracle model. In a quantum world, when proving post-quantum security, one usually needs the quantum random oracle model, where the adversary can query the random oracle with a quantum state. Typically, when proving security of a scheme, one usually construct a reduction that runs an adversary as a subroutine to break the underlying hardware problem. In the random oracle model, when proving the indistinguishability, one usually use a query-based reduction that use a hash query from the adversary to break the underlying hardware problem, such as when proving the FO transform, the React gem BR, OEP, and so on. In the quantum random oracle model, the quantum counterpart of query-based reduction is called measurement-based reduction that measures our query from the adversary and uses the outcome to break the underlying hardware problem. Reduction is called black box if it mainly uses the adversary's input-output behavior, while non-black box reduction requires the knowledge of adversary's internals, for example, adversary codes. Tight reduction with a smaller tightness gap are desirable for practice. For FO-like constructions from standard CP assumptions, tight reduction can be achieved in a black box manner in the random oracle model. However, all the quantum random oracle model reductions are non-tight, and most of them are measurement-based. In particular, the current black box reductions have a quadratic security loss. Although these quadratic security loss can be avoided by a non-black box reduction that relies on a newly introduced technique called measure running measure. But this technique can only apply to reversible adversaries. While the current black box reductions can cover arbitrary adversaries, this is quite different from the results in the random oracle model, where a linear security loss can be achieved in a black box manner. The quadratic security loss arises from the usage of the one-way-to hiding technique. The one-way-to hiding technique is an essential technique to prove post-quantum security of a crypto system. It gives a reduction from a search problem to a decision problem. Recently, several works try to improve the tightness of the one-way-to hiding. However, as in the case of FO-like CAMs, the tightness improvements are only restricted to the factor of reduction loss, and the quadratic security loss still exists. A natural question is that for FO-like CAMs and the one-way-to hiding technique, is the quadratic security loss avoidable for measurement-based black box reduction? In this paper, we give an affirmative answer for the above question. For FO-like CAMs, we show a measurement-based black box reduction from breaking the standard CPU security of the underlying PKE to breaking the CCE security of the resulting CAM will inevitably incur a quadratic security loss. Such an impossibility result can also be extended to the tightness limits of the general black box one-way-to hiding. The main technique is that we first construct a specific quantum adversary that breaks the CC security of the resulting CAM by querying the random oracle with a well-designed quantum state and solving a discrimination problem between two quantum states. The advantage of this specific adversary is at least square root p. P is a positive real. In using the meta reduction, we show that any measurement-based black box reduction that runs this specific adversary as a subroutine to break the standard CPU security of the underlying PKE will have advantage at most p. Combining these 2 points, we can get our results. This is a short summary of our work. Okay. Thanks for listening. Any questions?
Thank you for the talk. I don't see questions in the chat. Is there anyone that has a question or wants to unmute? Otherwise, I think we're already a bit ahead of time, so maybe we proceed to the next talk.
Okay, same. Thank you again for Haodong Jiang. So I would like to move to the next talk. The next talk is Redeeming Reset Indifferentiability and Applications to Post-Quantum Security by Mark Zhandry. And Mark Zhandry will give a talk. Mark, please.
Right. Can everyone see my slides?
Yes.
All right, great. So in this talk will be about indifferentiability. Indifferentiability is a strengthening of indistinguishability, which is used when you're trying to build one idealized object from another. Here I've diagrammed the case where you're trying to build a random oracle from a random permutation P and P inverse, also called an ideal cipher. Our goal is to justify that the resulting construction that we call C is in some sense as good as an ideal hash function, also called a random oracle. And indifferentiability is a way to formalize this goal. Indifferentiability can be seen as a form of universal composability for idealized objects. And indeed, Maurer et al. Show that indifferentiability composes well, and also that indifferentiable constructions are as good as the ideal object in the sense that it implies security in what are known as single-stage games. Single-stage games are games making up most of cryptography where a single adversary interacts with the challenger. Because of these nice properties, proofs of indifferentiability have become a popular way to justify the security of cryptosystems such as hash functions. For general multi-stage games, unfortunately, plain indifferentiability is insufficient. Multi-stage games are those like KDM security, deterministic public key encryption, leakage resilience, and so forth, where there are multiple adversary parties interacting with the challenger. For these kind of games, we instead need a strengthening of indifferentiability called reset indifferentiability, which looks basically identical to plain indifferentiability with the important difference that the simulator in the definition is required to be stateless. But there is an analogous theorem by Ristenpart et al. That shows that if you are able to have a stateless simulator, then you get composition and security in multi-stage games. Unfortunately, reset indifferentiability has some limitations. The main one being that something called domain extension is impossible. So domain extension is taking any small domain ideal object, like a small compression function, and constructing a large domain object such as what you would do with Merkle-Damgard. Or the sponge construction is also a version of domain extension, taking a small permutation, small ideal permutation, and constructing a large hash function. As domain extension has been one of the main applications of indifferentiability, this strong impossibility has more or less led to reset indifferentiability being abandoned with relatively few subsequent works in the area. So our starting point for this work is two observations. First, we observed that domain extension is not always necessary. For example, when using a random oracle to construct, say, deterministic public key encryption, if the size of your messages are bounded, then it turns out you only need a fixed domain random oracle. The second observation is that basically nothing is known about reset indifferentiability beyond the impossibility of domain extension. Prior work, somewhat surprisingly, didn't even establish whether you could shrink the domain, take a large ideal hash function and construct a small ideal hash function. Now, this seems like it would be trivial, but it turns out that doing this with a stateless simulator is actually not obvious. Other interesting open questions include whether you can build a fixed size random oracle from an ideal cipher and vice versa. So this leads us to our work, where we give a handful of new results on reset indifferentiability. First, we prove that domain shrinkage is in fact possible with reset indifferentiability using the obvious construction where you just sort of pad out the domain with zeros and then hash with the bigger hash function to get a small one. We also investigate the natural approach to building a random oracle from a random permutation, where you first pad the input and then truncate the output. You can think of this as the sponge construction for a single block. And we show that as long as the sum of the input and output lengths are at most the block length of the ideal cipher, that you get reset indifferentiability. On the other hand, we show that this restriction on input and output length are necessary. And by giving an explicit reset indifferentiability attack, if the input length plus output length exceed the block length of the permutation. And this is in contrast to the plain indifferentiability setting, where basically any non-trivial amount of padding and truncating will get you security. And then the final result is basically showing that all of our results lift to the quantum setting. And why this is interesting is that recent indifferentiability is actually very amenable to quantum proof techniques, and previous quantum indifferentiability results required sophisticated quantum machinery. On the other hand, we don't need this, and our proofs are relatively accessible. And as a consequence, we show that ideal ciphers in particular give random oracles, which was previously unknown quantumly, even if we were to ignore recent indifferentiability. So even under plain indifferentiability, this was not previously known. Right, so that's all I have, thanks.
Thanks a lot for the talk. Are there any questions in the Zoom chat? I don't see any. Just have to wait a second if there are some in Zulip. So up to this point, I've got one question. Maybe I didn't manage to read the paper yet, but is the idea to essentially reprogram the permutation, or?
Yeah, so in my longer slides, I have it diagrammed. So there's a couple here. Let me actually here. So there's a couple bits that are needed. So for domain shrinkage, basically what we need is a way to simulate the part of the domain that we're truncating, and we need to be able to do this without state. And basically what we show is that you can kind of steal part of the random oracle that the simulator has access to and use that as sort of as kind of a state that is immutable. And so we show how we can actually essentially get, if the simulator has access to a random oracle, that you can simulate additional random oracles, additional ideal permutations, or whatever you need in order to, fill out the domain.
Oh.
And then for constructing random oracles from ideal ciphers, what we need to do, what we basically do is we need to allow our stateless simulator to be able to answer the permutation queries, and importantly also the inverse queries. And the way we do that is we simulate the permutations in a way where in this sort of the junk part that we are throwing away, we actually encode using more ideal ciphers and random oracles and whatnot. We actually encode information about the input in a stateless way that allows the simulator to know how to invert it. And then our sort of barrier or our impossibility here is sort of essentially what it shows us that is necessary, that the only way you can simulate is if you can encode the input into this trash bits that you throw away. That gives the desired inequality.
I see. Thanks a lot. So there's no question anymore on Zulip. Then I would say we continue to the next talk. Thanks again.
Thank you.
Thank you. Okay, then I'd like to move to the next talk. The next talk is Franchised Quantum Money by Bhaskar Roberts and Mark Zhandry. I hope my pronunciation is correct. And the Bhaskar Roberts will give a talk. Are you ready?
Hi. So my name is Bhaskar, and today I'll be talking about some work that I did on quantum money with Mark Zhandry. Okay, so we are interested in studying quantum money, which seeks to use quantum states to create basically unclonable banknotes. This is not something that digital currency could achieve classically, but thanks to the no cloning theorem, we at least have hope that it's possible using quantum information. So in particular, the banknotes or the money scheme that we're designing should have two properties. The first is unclonability. This means that if an adversary is given n banknotes, they shouldn't be able to produce n+1 banknotes that all pass verification and look like valid money. The second property that we want is called local verification. This means that it should be possible for anyone, even an untrusted user, to verify the banknotes without communicating with the bank or any other trusted third party during verification. So we call this local verification because there's no communication that needs to be done to a far off trusted third party. So in particular, the field of quantum money has been interested in public key quantum money, in which there's a single public key that anyone can use to verify banknotes locally. So I'm interested in studying the quantum money problem because it seems foundational to the study of unclonable cryptographic primitives. In recent years, there have been proposals for a variety of unclonable primitives, such as copy protection, copy detection, etc. And these constructions generally use techniques that were originally developed for quantum money. And so my approach is, by developing really good techniques for the quantum money problem, hopefully they'll generalize and allow us to construct a variety of unclonable primitives. Any questions so far?
I don't think so.
Cool. So the state of public key quantum money is there have been a variety of attempts to construct public key quantum money over the past decade, but none of them have sort of succeeded in constructing public key quantum money from well-studied assumptions. There was a recent line of work that constructed public key quantum money from post-quantum secure IO, but of course we don't have constructions of that from well-studied assumptions. So this work takes a slightly different approach. We'll define a new form of quantum money called franchised quantum money, which is weaker than public key quantum money and easier to construct, but it achieves the two properties that we care about, which are unclonability and local verification. Previously, public key quantum money was the only primitive that achieved those properties. So the fact that we can achieve this without needing public key is surprising. The main idea is this. So in public key quantum money, verification is done using a single public key that anyone has access to, including adversaries. In franchised quantum money, anyone who wants to verify a banknote can get a unique secret key to use for verifying banknotes. So this means even an adversary could request a unique secret key, and the scheme would remain secure. So every key can be used to verify every banknote. And the security guarantee that we'll give is, as long as you keep your key secret, nobody can fool you into accepting an invalid banknote. To illustrate the difference between these two definitions, if you leak your key accidentally in the franchised model, in other words, if you make your key public, the security guarantees no longer hold, and it might be possible for an adversary to create a fake banknote that looks like the real thing when you're using that key for verification. Any questions?
I don't think so yet.
Cool. Also, people in the call, feel free to ask as we go along. Okay, so the construction that we give, I'll just summarize it at like 10,000 feet. Basically, when we try to construct public key quantum money, the problem that we generally run into is the verification key also gives the adversary enough information to counterfeit successfully. So our approach is to take this verification key, split it into lots of pieces, and then give each verifier one piece of the key. So in our construction, even having a single piece of the key is sufficient to verify the banknotes. But because an adversary given one key doesn't know any of the other pieces, it's hard for them to create fake banknotes that will fool verifiers using one of the other pieces. In a little bit more detail, our construction is based on the proposal for quantum money from hidden subspaces. So the master key would be a description of this subspace, which has n/2 dimensions. And in our construction, each franchised verification key is a small number of dimensions from that subspace. And so each verifier just gets a small random subspace from the hidden subspace. Finally, our construction requires a collusion bound. So this means that we guarantee that our scheme is secure, but only if like the number of colluding adversaries is O of square root n. What we find is that if multiple verifiers are dishonest, and if they collude and pool their keys together, they can learn quite a bit about the master secret key. And if there are more than square root n of them, they can learn the entire master secret key. So the collusion bound is a barrier to making this construction practical, but we believe it can be improved and even eliminated in future work. Cool, that's it. Any questions?
Thanks a lot.
Mm-hmm.
Do we have any questions? I don't see any in the Zoom chat. And Sulip, there's also nothing yet. So maybe in the interest of time, we move on because we still have 4 talks, I think.
Yeah, I think so. So if you have any talks on the talks, if you have any questions on the talks, please write them on the chat or the chat on Zoom. And so next, I would like to move to the next talk. The next talk is quantum computationally predicate-binding commitments with application in quantum zero-knowledge arguments for NP by Jun Yan. And Jun Yan will give a talk. Jun Yan, please.
Hi, thanks. So first, let me share my screen. Okay. Okay, can you hear me?
Yes, I can hear you and I can see your slides.
Okay, hey, thanks. Okay, let me begin. My name is Jun Yan from Jiang University. The title of my talk today is Quantum Computationally Predicate-Binding Commitments with the application in quantum zero-knowledge arguments for NP. Okay, so let me first state our main results. We know that from quantum scale 1V function, we can construct a quantum bit commitment that is in particular computationally binding. However, we know that with the general quantum binding, the committed value is no longer unique. It could be a superposition. So it's natural to ask what happens if we compose quantum bit commitments in parallel to commit a string, which is typical in application. We ask what binding property can the resulting quantum string commitment scheme satisfy? Is it useful in applications? This question has been open for almost 2 decades. And in this work, we make a first step towards answering these questions. So in particular, we prove the following so-called computational predicate-binding property. That is, any polynomial time bounded sender cannot open a commitment in 2 ways so as to satisfy 2 inconsistent predicates, respectively. And this is the first non-trivial quantum computational string binding that is both useful and can be instantiated with the minimal complexity assumption. And if we plug quantum bit commitments in Bloom's zero knowledge protocol, we obtain the first quantum zero knowledge arguments for MP solely based on quantum secure one-way functions, but with the soundness error of 1/2. And the main technical part of this work lies in establishing this computational predicate binding property. Okay, this is our main result. Now let me introduce 2 important concepts that are introduced in this work, namely pattern predicate and string predicate binding. They are motivated by the soundness analysis of Bloom's protocol, but we believe they are of independent interest and general enough in elsewhere. So for a pattern predict, first gene to satisfy such a predict, it should exhibit a certain pattern somewhere. And we remark that a witness might be needed to compute the pattern or where it locates in polynomial time. For example, we consider Bloom's protocol. The verifier's final verification induces 2 predicates, P0 and P1, corresponding to the verifier's challenge 0 and 1, respectively. For the predicate P0, the pattern is just the whole string. That should be the input graph after some permutation. With the soundness is just the permutation pi selected by the prover. For the predicate P1, the pattern is n1s that form an n cycle, and the witness is the location of a Hamiltonian cycle. These 2 predicates are consistent when the input graph G is not Hamiltonian. By inconsistent, I mean they are disjoint. No string can satisfy both of them simultaneously. With pattern predict, we can define predicate binding with respect to P0 and P1. Namely, if a sender can open commitments so that the revealed value satisfy P0 with probability 1, then it cannot open the same commitments so that the revealed value satisfy P1 with a non-negligible probability. Here, we highlight that now the revealed value could be a superposition of exponentially many strings with general quantum binding. Or put it in some quantum formalization, we need to show that accepting subspaces P0 and P1 that are induced by predicates P0 and P1 are almost orthogonal up to any polynomial time realizable unitary that does not touch the commitment space. And we say predicate binding if predicate binding with respect to any pair of inconsistent predicates. And the main technical difficulty lies in establishing predicate binding. One needed to try to avoid the potential exponential blow up of error that are incurred by this superposition of possibly exponentially many strings. And by our technique, we actually fail to prove the full predicate binding, but that are general enough for our applications. Okay, that's all what I want to say. Thanks for your listening. And questions are welcome.
Thanks a lot. Are there any questions? So maybe while we wait, if people add a question also for the previous speakers. Please check the chat every now and then to see, because there's at least one question for the first speaker that you could still answer in the chat then. By the way, you're still sharing. So we
okay.
see. Now you're showing the chat, which is actually good. But...
okay.
Okay, but I don't see any question right now. Then I would say we move on to the next talk. Thank you again.
Okay, thank you.
Thank you again. Okay, then let's move to the next talk. And the next talk is quantum encryption with certified deletion, revisited, public key, attribute-based, and classical communication by Taiga, Hiroka, Tomoyuki, Morimae, Ryo, Nishimaki, Takashi, Yamakawa. And Taiga, Hiroka will give a talk.
Okay.
Are you ready?
Yes. Can you see the slide?
Yes, I can see your slides and I can hear you. Yeah, please start.
Okay. Hello, everyone. My name is Taiga Hiroka. In this talk, I talk about quantum encryption with certified deletion, revisited, public key, attribute-based, and classical communication. This work is joint work with Tomoyuki Morimae, Ryo Nishimaki, and Takashi Yamakawa. First, let me explain the prior work. One-time secret key encryption with certified deletion was introduced by Broadbent and Islam in TCC 2020. In this primitive, there is a certified deletion security, in addition to the functionality of one-time secret key encryption. This security guarantees the following. First, sender generates a secret key and generates a quantum ciphertext and sends it to the receiver. After she sends a quantum ciphertext, if she changes her mind and wants to delete the ciphertext, she requests him to delete the ciphertext, and she receives a classical certificate, which guarantees that he deletes the quantum ciphertext. And then she checks whether this certificate is correct or not using her verification key. When correct, he cannot obtain the message M correctly, even if he receives the secret key of this ciphertext. Their construction has disadvantages as follows. First, their construction is limited to the setting of one-time secret key encryption. Second, in their construction, sender needs quantum operation. Third, in their construction, deletion is privately verifiable, which means that the sender needs a verification key kept secret. In our work, we have improved these disadvantages as follows. In this talk, I talk about quantum encryption with certified deletion, where the sender is completely classical. In our construction, we have used a noisy trapdoor call-free function F and injective trapdoor function G to construct a protocol. These functions are constructed from LWE assumption and have some cryptographic properties. Using these properties, a classical sender can generate a quantum state in the receiver's register. In a nutshell, idea of our construction is to use F-type function and G-type function instead of directly sending BB8 host states with quantum channel. Now, first, I explain how to use F-type function. First, a classical sender generates F-type function and trapdoor and sends function to a receiver. The receiver generates superposition state and coherently evaluates f of x. If he measures the third register in the computational basis, he obtains the measurement outcome y and the post-measurement quantum state. If he measures this quantum state in the computational basis, this quantum state collapses to the classical bit string. On the other hand, if he measures this quantum state in the DMAD basis, this quantum state collapses to the random classical bit string E and D that satisfies this equation. Noisy trapdoor call-free function F satisfies adaptive hardcore bit property, which guarantees that quantum polynomial time receiver cannot obtain both this and this at the same time with the probability more than 1/2. And in our construction, we have used the injective trapdoor function G in addition to this function. First, a classical sender generates function G and trapdoor and sends a function to the receiver. Note that from the injective invariance of this function G, quantum polynomial time receiver cannot distinguish this function from this function. This property is very important for construction. Then the receiver generates superposition state and coherently evaluates G of X. If he measures the third register in the computational basis, he obtains a measurement outcome Y and the post-measurement quantum state. If he measures this quantum state in the computational basis, this quantum state collapses to the classical bit string. On the other hand, if he measures this quantum state in the other basis, this quantum state collapses to the random classical bit string. Now I explain our construction. Note that this construction is not formal construction. If you are interested in the formal construction, please read our paper. First, a classical sender generates a random classical bit string as a secret key, where 0 denotes G-type function and 1 denotes F-type function. Then she generates these functions according to this classical bit string. At the same time, she generates trapdoor and sends them to the sender, a receiver. Receiver generates these quantum state and sends the measurement outcomes to the sender. At this point, she can know the post-measurement quantum state using measurement outcomes and trapdoor. On the other hand, he can't know the post-measurement quantum state from the property of these functions. Therefore, this process is as if a classical sender generates this quantum state in the receiver's registers blindly. Then she encrypts the plain text M using B1 X1 as follows, where H is a random oracle. After she sends these ciphertexts, if she changes her mind and wants there is a ciphertext, she requests him to measure all these quantum states in the demand basis and receives the measurement outcomes as a classical certificate. Then she checks whether this E and D satisfy this equation. When yes, he cannot obtain the information message M correctly, even if he receives the location of functions, which is a secret key of this ciphertext. In our work, in order to prove this construction security, we have introduced a new property of these functions, which we call cut and choose adaptive hardcore property. It is relatively straightforward to prove the security from this property. Therefore, I skip it. Instead of that, I explain an intuitive understanding of this property. Cut and choose adaptive hardcore property intuitively guarantees that when each E and D satisfies this equation, quantum polynomial time receiver cannot obtain B1 and X1, even if he receives the location functions after he obtains E and D that satisfy this equation. I explain the intuitive proof of our cut and choose adaptive hardcore property. In order to obtain these E and D, he has to measure these two quantum states in the demand basis. On the other hand, he cannot distinguish these functions. Therefore, in order to obtain these E and D with a high probability, he has to measure all these quantum states in the demand basis. On the other hand, if he measures this quantum state in the demand basis, this quantum state collapses to the random classical bit string, and he can no longer obtain B1 and X1 even if he receives the location function. This is an intuitive proof of our cut and choose adaptive hardcore property. Now I finish my talk. If you are interested in more formal these results, please read our paper. Thank you for your listening.
Thanks a lot for the talk. Are there any questions? So we've got nothing on Zoom. So Haodong answered Kathrin's question on the chat, but I also don't see new questions there. Then I would suggest we move on. Thanks a lot for the talk.
Okay. So I would like to thank again for the previous talk. And I would like to move to the next talk. And the next talk is Tight Adaptive Reprogramming in the QROM by Alex B. Grilo and Kathrin Hövelmanns and Andreas Hülsing and Christian Majenz. And Kathrin, I think Kathrin Hövelmanns will give a talk.
Yeah, hi everyone. Can you see my slides and hear me fine?
Yes, I can hear you and I can see your slides. Yeah, please start.
Okay, great. Thanks. Yeah, welcome to my talk about adaptive reprogramming and the quantum random oracle model. And before I dive into our results, I will first sketch the motivation of this paper. The motivation was random oracle model programmability, which is a nice property of the random oracle model that allows for simple proof strategies. And the strategy is as follows. We argue that if a random oracle has not yet been queried on a particular pre-image X, then the oracle value can be chosen on the fly by the game. And if we do so cleverly, we allow the game to be simulated by a reduction that then does not have to rely on secret knowledge, like, for example, a secret key. But unfortunately, the random oracle model does not suffice to argue quantum security, which is why it was generalized 10 years ago in a way that allows quantum access to the random oracle and hence allows to argue security against quantum attacks in classical networks. But with this generalization, there come some challenges. For example, any query to the random oracle might contain a pre-image X with some amplitude, and this might not be trivially checkable because checking would mean measuring and hence altering the state and potentially derailing the attacker. So an important question is, can we adaptively reprogram in the quantum random oracle model? And our results are in a line of work on this question, and a comparison will be given after I have shown you what we found out. So our result is a reprogramming toolbox, and I'll first sketch the simplest case of reprogramming, and then afterwards show how this result can be generalized. So what we consider is a distinguisher tasked with distinguishing between quantum access to the general random oracle H0 or access to its reprogrammed version H1. And the game goes as this. We have a distinguisher run in the reprogramming game. In the first phase of the game, it will have quantum access to the oracle H0 that is not reprogrammed. And at some point, it will issue a reprogramming instruction, and the game will pick a pre-image X and a random oracle value Y uniformly at random, and set the reprogrammed oracle to map X to Y and coincide with H0 anywhere else. Afterwards, the game will forward the pre-image to the distinguisher. And in the second phase, the distinguisher has either access to H0 or the reprogrammed version H1. And at the end, it has to output a guessing bit to indicate to which oracle it believes it had access to in the second phase. So classically, it's pretty easy to see that the distinguishing advantage can be upper bounded in terms of the number of oracle queries and the size of X, because to have any distinguishing advantage whatsoever, the distinguisher would have had to query H0 on X in the first phase. And our findings are that quantumly there exists a similar bound. Still, we have this fraction of number of oracle queries and size of X, but we have to consider square root and also multiply by a small factor. However, this bound is tight, as we have found a matching attack, which will be sketched in the YouTube talk. And now I can sketch how we furthermore generalized this result. So the first important generalization, of course, is that we want to reprogram many times, not just once. So we pick several reprogramming positions, X1 to XR. A second important generalization is that we now let the distinguisher determine on which positions we will reprogram by telling the game the distributions according to which the positions will have to be chosen. And the third generalization is that those distributions come with some additional side information that is also forwarded to the distinguisher. To compare with previous results, so none of the previous work considered any distribution that was anything else but uniform. And yeah, clearly this also means that the distributions did not offer any side information. And to compare the bounds, I just considered the uniform case to keep things pretty simple. So what we see here is that our bound improves by a small factor, and more importantly, it also improves by a factor of square root of Q. And with this toolbox at hand, we can also, we were also able to give some security proofs in the quantum random oracle model. So we improved on previous work on VHME signatures and the message compression routine of XMSS, because we now have this toolbox that allows for conceptually simple proofs and also is a bit tighter. And we also gave the first proof in the quantum random oracle model that the hedged VHME construction is secure against several fault injections and nonce misuse. Yeah, and with that, I want to conclude my talk, and I'm happy to take any questions.
Thanks a lot. Nice talk, great result. Are there any questions for Kathrin? So I don't see any question in the Zoom chat. I also don't see any question in the Zulip. Now there's a question in the Zoom
there's
chat.
A question.
Thank you for your talk. Does the bound get worse in the non-uniform case?
Yeah, a nice question. The answer is no. This will also be presented in the long version. So let me go back to the slide with the bound. Yeah, so here we see a fraction of Q over the size of X, and 1 over the size of X represents the uniform distribution that I picked. And what we would consider instead, if we go to the non-uniform case, would be the maximum probability of any of those distributions hitting a particular element. This is all that changes.
Okay, is there any further question?
If there is no question, I would like to ask one question. So I think about the bound for non-uniform case. Maybe, I'm sorry, I may missed something. So do you also get the tight bound for non-uniform case?
I'm not sure. So we didn't prove tightness of a bound for the non-uniform case. We only proved it for the uniform case, I think.
Oh, and do you think there are any interesting things about considering about tightness for non-uniform case? Or do you think you are not so much interested in, no, sorry, it is not so interesting to study the tightness for non-uniform case?
I think that's a very interesting question. It was just out of the scope of this paper because it was already very long because we had to include all those security proofs.
I see. Okay, thank you.
Oh, maybe I can add that I would expect the non-uniform case also to be tight. And I think it should be possible to prove that by reducing it to the uniform case via some kind of asymptotic equipartition property. So by taking many copies of the non-uniform case.
Oh, interesting. Thank you. Thank you.
Thanks a lot. Then, yeah, I guess we can move on to the next talk.
Okay, then I'd like to move to the next talk, the last talk of this session. And the next talk is QCB, Efficient Quantum Secure Authenticated Encryption by Ritam Baumik, Xavier Bonnetan, André Chailu, and Leighton Luhon, and Maria Naya Plasencia, and André Schrotten-Roja, and Yang Xuran. And Ritam Baumik will give a talk. Are you ready?
Yes, thanks, Akinori, for listing for the introduction and for listing all the authors so that I can jump straight into the talk. Okay, So we begin with OCB3, which is a very popular authenticated encryption mode. And it just uses these offsets, which are calculated based on an IV and the block number. And it uses these offsets with the ECB mode, which is highly parallelizable. And this makes it very lightweight, and it's a rate 1 authenticated encryption mode, which means it just uses one block cipher call per message block. So we begin with this, and we want to examine how it stands up against a quantum adversary. But unfortunately, there are results already that this is not quantum secure because there are many periods. For instance, if we encrypt the same message block twice and then XOR the ciphertext, then this becomes a periodic function of the message block because the IV part of the offsets cancels out. And this, since the period is constant here, we can use Simmons to recover the period, which is delta 0 XOR delta 1. And from that, we can do a forge easily. And this is just for the ciphering part. But on the tag part as well, there can be attacks, because if we just encrypt, if we just calculate the tag of the empty message and with the same associated data block repeated twice, then the tag becomes a periodic function of the associated data block with a constant period. And again, we can use Simmons. So these are known results, but we are interested in the rate 1 property of OCB3. So here we try to examine how we can fix these weaknesses of OCB3 and still get a rate 1 authenticated encryption mode, which is secure against a quantum adversary. So the first idea is that maybe the offsets are bad, because in OCB3, the offsets consist of something from a component from the IV XOR with a component from the block. And this means that when you XOR the offsets on 2 successive blocks on the same IV, the IV component gets cancelled out. But we could modify this, and we could take, for instance, offset which is I.ekiv, and then this IV part does not cancel out when you XOR it over 2 blocks. But unfortunately, there is a Simmons-based attack that still works on this, because if you take one single message with the same IV and then take the same, if you repeat the message block, each message block twice, like in 1, 2, 3, 4, and so on, and then if you take the XOR of this ciphertext, they have the same period, and then you can use something like a Simmons to sample vectors which are orthogonal to these periods, and then you can extract enough data to solve for ekiv. So this does not work. And this leads us to believe that the main problem in OCB against the quantum adversary is the O part, the offset part. And so we want to modify it in a way that these the data on IV and block number is still used, but not as offsets. And so we move on to QCB, and where we do some kind of domain separation. So essentially we use tweakable block ciphers. And this was an idea used already in something called ThetaCB, which was used in the security proof for OCB3. But here we see that if we process the tweak in some other way, not using these offsets, then we can get the good quantum security of this construction. So this is QCB. It's essentially the same construction, except we abstract out the offset part and put everything into a tweak, which has the IV, the block number, and something for domain separation. But for processing the authenticated data, for processing the associated data, we use something else. We use the IV as inside the tweak for the block cipher calls for processing the associated data. And this is something different from OCB3, where the IV is not used for the edit. But this, as it turns out, to avoid quantum linearization attacks, it is necessary to use this chain. And so this is what is broadly called QCB. And for the tweakable block cipher, we want something that is secure against the quantum adversary. And if we assume a perfect quantum security on the TBC, then we can show that this is also very secure authenticated encryption mode. But then we explore further. We try to explore some actual TBC, which can help us instantiate this QCB. And for this, there can be several TBCs. For instance, there is a TBC with 3 block cipher calls per TBC call by Yamada and Iwata. But we want to use something that is rate 1, because otherwise our construction is no longer rate 1 on the block cipher. But we found that the key tweak insertion TBC, where the tweak is simply XOR with the key, actually works quite well for our purpose. But there is a caveat that we could not prove ideal TBC security on the key tweak insertion. And we had to make the modification that the tweaks have to be non-adaptive. So that is a modification we have. And by the way, in this model, the tweaks are also classical. And that is a common use case, and we use that here. So the tweaks are classical and non-adaptive in our proof. And with that, we can show that our QCB has these goals where these popular notions of privacy and unforgeability are used. For privacy, we say it's int QCPA, but with the modification that the IVs are either random or specified in advance. And this is to take care of the modified security of the TBC. And for unforgeability, we use the Bonnet-Zhandry notion, but with the modification that the IVs are either random or specified in advance. And with these modifications, we are able to prove the security of QCB when instantiated with the key tweak insertion TBC. Okay, and that is the main result of the paper. And there are several open questions which we can explore, like whether we can show in QCC security, whether we can define it properly, and whether we can show it, and whether we can use the more recent definition of blind unforgeability, and whether we can show the full TBC security of the key tweak insertion, and finally, whether we can say anything without the ideal cipher model. And the full version is found on ePrint, and there is also a longer version of this talk on YouTube. Thanks for your attention, everyone.
Thank you, Rita. Are there any questions? So I know it's quite early for people, but
if there is no other question, I have one. So I'd like to ask a question.
Yes.
So if in your work, so you assume nonce are random or specified in advance, right?
Yes.
So what happens? So what happens if you repeat the nonce, or nonce is chosen by adversary? Both of privacy and authenticity broken immediately?
No. So if the nonce is repeated, then there can be problems. The proof doesn't work at all. And if the nonce is not repeated, but it's not declared in advance, it's chosen adaptively, then I mean, we have a hunch that this is still secure, but we could not prove it because we could not prove the security of full ideal TBC security for the TBC. But no, the nonce repeating is probably, I mean, we did not show an attack, but our proof relies heavily on the fact that the nonce is not repeated.
Okay, thank you.
Maybe I can also ask a question. Thanks for the talk, Rita. So I was wondering whether you think your proof techniques are fit to prove blind unforgeability, or whether you whether other different techniques are necessary.
No, so our proof techniques are somewhat more ad hoc than we would have liked, but I mean, in these proofs, what the impression we had was that there are still no standardized framework for making these proofs. So some people are trying to standardize the database method, for instance, which would give us some sort of counting proofs which can be put into a standard framework. But here we use somewhat ad hoc arguments for the proof. So yes, so for that may be generalizable to blind unforgeability, but for that our main problem was, I mean, we could not clearly define the problem, or we were not sure how to use it. So what I'm trying to say is that the proof techniques we used were not very generalizable.
Okay, thanks.
Okay. And I guess thanks a lot for your talk. And that was the last talk in the session. So I think we got about a 30-minute break now. We're even 3 minutes early. And then there is the Test of Time Award happening at 10 past the full hour, wherever you are. It will be a bit later or earlier than for us. Then have a nice day and see you in half an hour.